Okay, we're going to look at minimum cost spanning trees by looking at three algorithms that help us to determine spanning trees, shortest path algorithms. That is our focus in this session. The minimum cost spanning trees started with a pictophone problem. Now, what a pictophone is it's a telephone service that provides video images of the callers, pretty much how people in boardrooms meet lately on Microsoft meetings or Google meetings, whatever the case is. Okay, so let's not wait any longer. Let's see what this is about. There we have a familiar graph that we used before, but this graph represents the possible links that might be included in a pictophone network, with each edge showing the cost in millions of dollars to create a particular link. To send a pictophone message between two cities, a direct communication link is not necessary, because you could connect, let's say, city B and city E via city A, C, or city D. It depends on which one is the minimum cost to establish, which connection will cost the least. So this is a totally connected graph. It's a complete graph, so it's a graph K5. There's 5 vertices, yes. And each edge represents the amount in millions of dollars to establish a link between the cities. So we assume the cost of the relay of a message compared with the cost of the direct communication link is so small that we can neglect this amount. The problem that concerns us, therefore, is to provide a service between any pair of cities in such a way that it minimizes the total cost that we use to establish such a link. Okay, so let us see what this entails. Joseph Kruskal is a mathematician that lived from 1928, and you can see Joseph passed away in 2010. In 1956, he formulated Kruskal's algorithm. Now, folks, you can see how fresh and how new the work is that we're working with. Kruskal's algorithm said the following: we add the links in the order of cheapest cost so that no circuits are formed, and so that every vertex belongs to some link that we have added. That is Kruskal's algorithm. So what do? We add the links in order of the cheapest cost. Now, where did we hear that before? Can you remember in the previous one we had to order the edges according to their weight, and that was called the sorted edges algorithm. Okay, so we sort them from cheapest, and then we start adding so that we do not form circuits, so that every vertex belongs to some link of sorts in the graph that we're working with. Now, Kruskal's algorithm, like the minimum or the sorted edges algorithm, is a greedy algorithm. It finds the minimum spanning tree for a connected weighted graph. Now, that's a lot of new words that we're learning here in our graph theory, but we'll pay attention to that just now. This means it finds a subset of edges that forms a tree that includes every vertex, where the total weight of all the edges in the tree is indeed a minimum. If the graph is not connected, then it finds a minimum spanning forest. So what is that? It's a minimum spanning tree for each connected component of the graph. Now, you can read more about that on Wikipedia if you search for Kruskal's algorithm. Now, let's go back to the pictophone problem. I've just colored the edges in different colors so that we are sure that the weight that are assigned on the graph belongs to the particular edge that carries its color. Okay, so our first guess at a solution is to put the cheapest possible links between the cities first, until all cities could send messages to another city. Such an approach is analogous, as we've said, to the sorted edges algorithm that was used to study the traveling salesman's problem. So if we sort the edges are from 0.5, the least cost, up to 1.6, the most expensive edge. If the cheapest links are added until all cities are joined, then we have used the first 5 edges. Okay, so there's 5 vertices. To make sure all the cities are joined, we're going to use the first 5. Now if we look at that graph, having used the first 5, the cities are linked in order of increasing cost until all the cities are connected. Now we can see that there's a problem, folks. At EA, we have formed a circuit by connecting EA as well. Now it is the third most cheapest edge to cities to connect, or edge to form on this graph. So we were now going to skip that edge and delete it from the graph, so that we now have a minimum cost spanning tree. The order in which we selected them is given by the numbers that are shown on the graph at the top over here. We first selected that one, then this one. We thirdly selected it, but it was a circuit there, so we deleted it. That was the third side, and then the fourth side was the side DC. Okay, so given a connected, that's one thing that we must have, is a connected undirected graph. A spanning tree of that graph is a subgraph that is a tree and connects all the vertices together. A single graph have many different spanning trees. We can assign a weight to each of the edges, which is a number that represents how unfavorable or how favorable that weight would be, depending on what it is that we looked at, and use this to assign a weight to the spanning tree by computing the sum of the weights of the parts of the tree. Now a minimum spanning tree, or a minimum weight spanning tree, is then a spanning tree with weight less than or equal to the weight of every edge in the spanning tree. So more generally, in an undirected graph, not necessarily connected, has a minimum cost spanning forest, which is a union of the minimum cost spanning trees in the graph with connected components. For its connected components, actually. Read up on that on Wikipedia as well. Very interesting information. In Kruskal's procedure, though, as in the shortest edges for the traveling salesman's problem, the edges that are added need to be connected to each other until the end. Okay, so a subgraph is formed in this way, and this will be a tree. That is, it will consist of one piece and contain no circuits. Remember, trees do not contain circuits. It will also include vertices of the original graph that we had. So, okay, if the subgraph is a tree that contains all the vertices of the original graph, then it's a spanning tree. So you might have a graph with 10 vertices. You only have connection between 8 of them once. That will be a tree of the initial tree, of the initial graph. So it's a subgraph of the initial graph. But if your tree connects all the vertices once and once only, then you have a spanning tree for the graph. So let's look at examples. We have that graph. If we look at the wiggly edges, the blue edges on the graph there, then we can see that we haven't included the vertices D and E. So in relation to the original graph, that is only a tree in the original graph. It's not a spanning tree because it does not include all the vertices. Okay, so that's not a tree. It's a tree but not a spanning tree. Our second graph, look at that graph. We've connected A, B, C, D and H, but there's a disconnection between that and the last 3 vertices. So separately, those 2 wiggly connections are trees which form a forest in the initial graph. Okay, so in relation to the initial graph, it's a forest that consists of 2 trees. Let's look at the third graph. If we look at the third example there, it's very clear that we have connected all the vertices, but A, B, C, D forms a circuit. So it's not a tree nor a spanning tree of the initial graph. So there's our cases again. The first one is not a tree because it does not connect. It is a tree but not a spanning tree because it doesn't include vertex D and E. The second graph is a forest consisting of 2 trees. It's not a spanning tree in the top, but the third one also forms a circuit, which means it's not a tree, so it can't be a spanning tree. So let's look at one that is a spanning tree. If we look at that graph at the bottom, it connects every single vertex without having formed a circuit. So it does what Kruskal's says it must do. So it is indeed a spanning tree of the initial graph. Okay, so let's look at this one. An example. Now we're adding weights to the graphs. Previously, you'll see we didn't have weights. We just discussed them in general. Now we have weights to each little edge, or to each edge in that network. Okay, so let's say that represents, there's a new suburb that's going to be developed, and that represents the cost that we're going to incur by developing roads in a road network in this new development. Okay, so what we are going to do is we're going to find the minimum cost spanning tree for this graph. So what do? We start with applying Kruskal's algorithm. We add the edges in order of increasing cost until we have created a spanning tree. So it makes sense to start at A, B and E, I first. We've colored them red because their weight is 1. The next weight is 2 between G and H. We still have not got a tree or anything going here. So let's go and add the next weights, which will give us 3. Okay, so far not all the vertices are included, so we add the next set of edges. There's 4 edges with a weight of 4, and look at that. We only have one edge or one vertex to still visit, and this is L here at the bottom. And the cheapest way to do it is not from K to L, but from H to L, because the weight is indeed 6. Okay, if I remove, that's what it looked like. I remove the edges we haven't used. You can see clearly that that is a minimum cost spanning tree. Okay, now we can find the weights. The weight of that M, the minimum cost spanning tree, but just adding the total number of weights gives us a cost of 35. So the tree is the cheapest one that makes it possible to drive between any pair of homes, if A, B, C, D and those are homes in this new development. Okay, so to get from A to F, you've got to drive a little bit more. But we only built those roads because that was the cheapest cost to cover the whole network. Okay, I want you to try the same for this graph. So start with this graph, start with the applying Kruskal's algorithm. Pause the video and then we'll see if you are correct. Okay, let's see what you've done. Well, the minimum cost here is definitely going to look like that. We started at 1, the next was the 2 here at the bottom, so we added this edge, then we would add the 2's there, we would add the 3's, the 4, the 7 and the 8's, and in no incident, we could have formed by adding a 4 here, we could have formed a circuit, so we did not use that 4. We could have then added 5 here, which formed a circuit, but we said we don't want circuits. Here we could have used the 4. There was a possibility of a circuit again. And if we had used the 6 and the 4 was used, or the 6 there with those 4 sides, it would have been a circuit. So we chose selectively applying what Kruskal says we should do. Okay, the total weight for this graph is indeed 30. So let's look at another algorithm. Now remember, Kruskal uses edges. We're going to use Prim's algorithm for the minimum cost spanning tree. What does Prim do? Prim says choose a vertex at random to start with. So Prim works with vertices where Kruskal works with the edges. He says choose any vertex at random. Well, if you look at a graph, it will make sense to start at the vertex that has the least cost edge connected to it, but we don't need to start there. We can in fact start anywhere on the graph. Find the edges from this vertex that connect the tree to new vertices. So if you are at vertex A and it has adjacent vertices E, F and G, you look at all three and you choose the side that has the least cost. Continue this process until you have a spanning tree. So let's return to that graph that we had. We're going to find a minimum cost spanning tree using Prim's algorithm. So I'm going to start at that vertex there, that's colored red. That vertex has four adjacent vertices. The weights are 3, 4, 10 and 18. Clearly the cheapest is 3. So I choose that path first. Then I'm at the next vertex to the left. That is adjacent to 3 other vertices. The cost being 1, the cost being 5 and the cost being 9. So I'm going to choose 1. Now I'm at the vertex at the top. If I look at that vertex, it is adjacent to only one unused vertex, and that's the one to the left. So I choose that vertex. Then I have a choice of 3 new ones to move to. The weights are 9, 9 and 7, so I choose the cheapest one, which is 7. I'm at the bottom vertex now. It has 3 adjacent vertices that has not been used. It's actually adjacent to 5, but 3 was actually 6, but 3 has not been used. The weights being 8, 8 and 9, so I can choose the 2 8s, because clearly that's the next weight that I need to focus on. If I move to the vertex over here, I see it is connected to 2 other vertices on its left, each with a weight of 2, so I choose those 2 vertices. Then there's one unvisited vertex here. Well, if I go from there to there, it's 6. If I go from here to there, it's 9. If I go from that vertex to the last vertex, it will have a weight of 3. There's my minimum cost spanning tree using Prim's algorithm, and look at that. The weight is indeed the same as what it was when we used Kruskal's algorithm. Okay, so I hope it makes sense to you of how Prim's algorithm works. Kruskal works with edges, Prim works with vertices. Now let's look at this tree, and we're gonna pause the video at this stage for you to apply Prim's algorithm for a minimum cost spanning tree and see what you get. So pause the video and then come back. Okay, let's see what you did. First of all, you chose the edge. But if we start at C, it's not the vertex with the minimum edge, but I'm trying to make a point now. So CD has a weight of 2. Then we add D. D is adjacent to E and B, so we choose the cheaper one, which is 4. E is adjacent to A, G and F and also B. B doesn't have a weight on it, so I'm going to choose A. Okay, now I'm at A. The only adjacent one, though, the cheapest one to choose is indeed B. I'm at B now, so I can't choose D or C because then I will have a circuit. So I move back to A and I chose G. From G then, if I go to E, I form a circuit, and if I go from G to F, I form a circuit as well over there, so I'm not going to choose any one of them. There's one unvisited vertex, and that's the one here at H. So from H, I go from F to H, which has a weight of 5, and my minimum weight here is going to be, or that's going to be my spanning tree, and my spanning tree here will have a weight of 20. So certainly you got the same result as what I did when I did my version of the minimum cost spanning tree using Prim's algorithm. Okay, so let's look at a shortest path algorithm now. In a shortest path algorithm, we map out the shortest path between vertices on a graph, getting from one point to another point. The person that gave us the tools to do this is Dijkstra. Dijkstras Algorithm is an algorithm to find the shortest paths between nodes in a graph, which may represent, for example, road networks. Dijkstra was a Dutch computer scientist, Edgar W. Dijkstra. He formulated this algorithm in 1956. And that's a photograph of Dijkstra in the year 2002, again making the point, folks, that we are working with such fresh mathematics, it's unbelievable. Dijkstra's algorithm works as follows. It picks an unvisited vertex with the lowest distance, it calculates the distance through each of the unvisited neighbors, and update the neighbors' distances if it is smaller than the distance that's already at that node. It marks visited vertices when we are done with neighbors. So that's a lot, and I said that quite quickly because I'm sure you don't understand exactly 100% what Dijkstra said, so let's have a look. Dijkstra's algorithm works as follows. You mark the nodes unvisited, all of them. Create a set of all the unvisited nodes called an unvisited set. Number 2, you assign to every node a tentative distance value. You set it to 0 for our initial node and then infinity for all the other nodes on the diagram. For the current node, you consider all the unvisited vertices. So here's my initial node. I consider all the unvisited vertices around the initial node and I look at those weights. I record that weight, this weight, and this weight. The least of the 3 weights I mark off. I mark this node as visited and that node as visited, and then I continue that journey. I repeat it. Here it says compare the newly calculated tentative distance to the current assigned value and assign the smaller one. For example, if a node A is marked with a distance of 6 and the edge connecting it to its neighbor has a length of 2, then the distance through to B through A will be the sum of those two, which is 8. If B was previously marked with a distance, let's say 11, then we will discount that distance, cross it out, and we will record the 8 because that is the shortest path. Otherwise, we will keep the 8 if the distance that we now have is more. Okay, so when we are done with considering all of the unused neighbors of the current node, mark the current node as visited and remove it from the unvisited set. A visited node is never to be checked again. Okay, if the destination node has been marked visited when planning a route between nodes, or if it's the smallest tentative distance among the nodes in the unvisited set is infinity, then we stop. The algorithm is finished. Okay, so otherwise select an unvisited node and repeat this process. Let's see how it works. We use Dijkstra's algorithm to find the shortest path between vertices A and D. So our initial vertex will be A. We set that vertex to 0 for our initial node and infinity all the others. So you'll see the node is marked with green. It is 0 away from itself, so we at the node. Now we look at its neighbors, which is B and F. Okay, the nodes that are adjacent to A. We calculate their tentative distances through node A, compare the newly calculated tentative distances to the current assigned value and assign the smallest one. Now you'll see at B and F there's infinity, so certainly everything that we are going to see on the graph is going to be smaller than that. So the distance from A to B was 2. So I record a 2 at B, I record a 5 at F. Of the two, B is the smaller one, the smaller weight. Okay, so I go to B and I have a look. The two adjacent vertices will be E and C. So if I go from A through B to C, it's 2 plus 7, which will make that infinity a 9. From A through B to E, which will make this infinity a 6. Okay, that is what the algorithm says we have to do. So I record those two tentative distances. From B to E, the cumulative distance is 6, and from B to is actually 9, and from B to C, the cumulative distance is 9. Sorry, from B to E it's 6, and from B to C it's 9. So we mark the smaller one as visited, which is 6. Now we are at 6. Okay, we do the same. So from E to C, in 6, the cumulative distance will now be that 6 plus this 3, which is 9. We already have a 9 at C, so that 9 is going to stay what it is. Now we want to visit F. So we go from A to B to E to F. There's already a cumulative distance of 6, plus that will give me a 9. Yeah, the 9 is larger than the 5 that I already have, so I leave the 5. The other vertex that is not visited will be G. So the cumulative distance there will be 2 plus 4, which is 6, plus 5. This infinity there is therefore going to change to 11. Okay, we've got one more node to visit, but we are not going to go from G straight to D. We're going to look at those two nodes which are adjacent here. So if we compare these three here, the shortest or the smallest is 5, but we've already visited 5, so we're not going to visit it again. Remember, the algorithm said once something is marked visited, you don't go back. Okay, so the only two that we're considering here is C and G. The smaller one is C. It carries a weight of 9. So from C to D, I will have a weight of 9 plus 8, which is 17. Okay, we mark it as, sorry, that's just what I've spoken about. We've marked 9, the infinity, as 9 plus 8, which, sorry, I've started at G. 11 plus 7, which is 18, but 9 plus 8 is indeed 17, which is less. So we change this node to a 17. And there we've continued our journey. We can mark it as visited node D, and that gives us the minimum distance, or the shortest path between from vertex to get from vertex A to vertex D. Now the shortest path is 17. Let's see where it comes from. It comes from A to B is 2, B to E is 4, that's 10. Where do we go from there? We go, no, let's go the other route. We go from A to B is 2, B to C is 7, that's 9, plus the 8 is 17. So our shortest path is AB, BC, and CD, and it's a path that has a weight of 17. Notice that we have found every shortest path between vertex A and every other vertex in our graph. We have found the shortest path. We were just looking, the question was saying go from A to D in the quickest possible way. Okay, so Dijkstra's algorithm, folks, where is it applied? It's applied to automatically find directions between physical locations, such as driving directions on websites like MapQuest or Google Maps. Even if you have a GPS system and you want the shortest path, it uses Dijkstra's algorithm. It also is used in a network of telecommunication applications. Dijkstra's algorithm has been used for solving minimum delay path problems. For example, in a data network routing, the goal is to find the path for data packets to go through a switching network with minimal delay. Okay, it's also used for solving a variety of shortest path problems arising in a plant and facility layout robotics, transportation, etc. Okay, so that is Dijkstra's algorithm. You can see there's a map of America. To get from New York or Cincinnati to Minneapolis, for instance, there is a shortest path. So it looks at all the pathways available and it maps out that path. Here's a nice quote from Dijkstra. Dijkstra said, "Programming is one of the most difficult branches of applied mathematics. The poorer mathematicians had better remain pure mathematicians." Now that is a very, very powerful statement. Okay, this is what graph theory does. It's an applied mathematics. Okay, you can apply it to so many things. We've seen it so far. We can solve the Chinese postman problem. We can solve the traveling salesman problem using graph theory. Every single real life problem can be represented by a graph. Okay, let's look at a few more examples of applying Dijkstra's algorithm. Okay, we're going to use Dijkstra's algorithm on 2 or 3 more examples. Okay, let's start. We're starting here at vertex A because we can see it's been set to 0. Every other vertex has been set to infinity. Okay, so what is adjacent to A? Adjacent to A, we have those 3 vertices. This one has a weight of 3, so we will record, let me just get my pen there, we will record a 3 there instead of an infinity. Here we will record, because it's the first time that this vertex is visited via that edge, a 7, and here we will record a 5. We mark this one as visited, and then of the 3 we choose the one with the lowest weight to continue with. Now this is adjacent to 2 other vertices. We're not visiting this one because Dijkstra said once it's marked as visited, we don't go back. Okay, so from there to there we need to travel an additional 7. So that makes this vertex 10. But here look at what happens now. From 8 to there we got 7. But if we go from here to its neighboring, it is 4. So the 7 gets erased and we replace the 7 with a 4. Okay, so of the 2 here, of the 3 actually, this one is the one with the smallest weight. So we're going to mark it as visited. Okay, now let's see. If we go from 4 to its adjacent vertices, there's 1, 2, 3, 4 vertices that are adjacent. If we go to the top one first, we see it's 4 plus 2, which is 6. Now Dijkstra said if the number is less than the number that's already there, we replace the higher number with a lower one. So the 10 goes away and I bring in a weight of 6. Oh, that's a terrible 6, but yeah. Then we move to our next vertex, which is over here. We've already have a cumulative distance of 4. If I add 1, then this will have a weight of 5. Okay, that 6 bothers me, so I'm just going to try and make it a more acceptable 6. There we go. It looked too much like my 5. Okay, so I visited those 2 ones. I'm going to visit this one now. 4 plus 3 is 7. 7 is less, oh my pen, 7 is less than infinity, so I record a 7. From here to this adjacent vertex, I have 4 plus 3, which is 7. There's already a number that is less than 7 recorded over here, so I am leaving the 5. Now of the 4 new vertices, there's 2 5s. So let us mark this one visited and let's work on from there. The only unvisited vertex from here that's not marked visited is indeed this one. So 5 plus 2 is a cumulative distance of 7. There's already a 7. So I'm happy with that one. If I move to the other 5, if I go to its adjacent vertices, which is that one, this one, and that one collectively, let's start there. If I go up to the 6, it's a distance of 5 plus 2, which is 7. There's already a 6 there. The number is less. If I go to this vertex, it's 5 plus 3, which is 8. There's one that's less than 8, so that one stands. If I go to vertex B, I've never been there, 5 plus 2 gives me 7. If I go to the vertex over there, then I get there with a cumulative distance of 8. Okay, so I can mark this one as visited, the least one. Then I go to, out of the ones that are not marked visited, I go to the lowest one, which is 6. Okay, if I look at 6, if I go back here, it's 8, there's already a 5, I'm happy. If I go to this adjacent vertex, I add 1 to the weight, which takes the 8 and it turns the 8 into a 7, because the 7 is less than the 8. Okay, and that's the only thing that I can do there, so I can mark this vertex as visited. Of the remaining vertices, all of them have a cumulative distance of 7. So if I start with this one, and I go to B, I have to add 5, which will make this 12, which is more than what's already there, so I ignore it. I can't visit there, so I can mark this one visited. Let's go to the vertex over here. If I add it, I can't visit any of these neighbors because they've already been visited. And I go to B, I see it's a distance of 11, and I don't want 11 because there's already 7. So I'm finished with that one, and that takes care of traversing the graph. Okay, so the minimum distance to get from A to B is indeed 7. Now we can find out how that distance is reached. Let's have a look. There's 3, 4, 5, 6, 7. The minimum distance from A to this vertex is also 7. Let's see how that is reached. We go 3, plus 1 is 4, plus 1 is 5, plus, not the right choice. So 3, plus 1 is 4, plus 2 is 6, plus 1 is 7. So we've got the minimum distance between every other vertex and the initial vertex of A, which was 0. Okay, so let's do one more of these. Let's look at that graph. Let me just get rid of all the markings that I've made here on the screen. Okay, so this question asks us the following. It says, run Dijkstra on the following graph and determine the resulting shortest path tree. Okay, so let us start. Let's choose a vertex. Let's start at vertex A. There's a lot. Oh, hang on. This is a directed graph. So there's direction that we must move in. Okay, so we can only move from S to the others. So let's set this one to 0, and every other one we're going to assume is infinity. That's what Dijkstra instructs us to do. Every other vertex that is not visited yet is infinite. Okay, so we start at S. There's 3 adjacent vertices. If I move from S to A, I have moved a distance 3. So that becomes a 3. If I move from S to C, I've moved a distance of 2. And from S to F, I've moved 6. So I can record the 2 there, record the 6 here. I mark this vertex as visited. The lowest between these 3 is vertex C. So to get from C to A, I need to add another 2. So that gives me a 4. There's already a 3, which is less, so I'm happy. To get from C, can't go back here. To get from C to D, I need to add 3 to the already used 2. So that will change the infinity to a number that's smaller than infinity, which is 5. And there's no other adjacent vertices to visit, so I can mark C as visited. Now between 3, 5 and 6, 3 is the one with the smallest weight. So I go to 3 and I apply the algorithm. From 3, from A to B, I've already moved 3 from S. So I add another 6 and that infinity disappears and has a smaller number of 9 recorded at that vertex. Okay, then I move to this adjacent vertex here, which is D. If I move from A to D, I've already moved 3. I move an additional 1. There's a 5 there, so I take the 5 away and I record it with the smaller number, which is 4. 3 plus 1 gives 4. Okay, that's the only adjacent vertices to A, so I can mark A as visited. There's these 3. I go to the lowest one, which is 4. 4 is only adjacent to E, so that would mean I need to add 4 and 4, and I can record an 8 over here, and I can mark this one as visited. I now have 6, 9 and 8. The smallest is indeed 6, so I go to 6. 6 plus 2 is 8. I'm happy. It is already an 8, so I leave it an 8, so I mark this one as visited. 9 plus 1 is 10. That's the only vertex. Oh no, sorry, I can only go to 9 because I'm only allowed to move here. So if I add 1 to 9, I get 10, which is not what I want. I'm going to leave it an 8. That is visited, and there is my algorithm of Dijkstra applied to find the shortest path tree in this diagram. So if I want to move from O to E, the minimum distance is indeed 8. Let's see how I move. I move from S to A, which is 3, from A to D, which is 1, which gives a cumulative distance of 4, and then from D to E, which produces the 8. That's one way. I could have gone from S to F, which is 6, and from F to E, which is another 2, 8. So I could have moved that direction, or I could have moved this direction. It would make no sense to move the other direction, to move over there, because already I have a distance that is higher than the one that I wanted. Okay, so let's see, is there another path? Yes, look at this. There's 2 plus 2 is 4. No, but that's not one of the minimum paths that I'm going to take, so I'm going to leave it at that for now. Okay, so there's my algorithm of Dijkstra applied to that graph. One more graph, and I think then we will call it a day. I'm going to put the graph on, and I want you to try and find the minimum shortest path tree in this graph, okay, by applying Dijkstra's algorithm. Pause the video and do this, and then we'll see how you fared. Okay, let's start. We're going to start at vertex O. Okay, so we're going to mark this one as 0. Everything else is infinite. I'm not going to put them in. I'm just going to assume that we have infinite there. Okay, so from 0 to this vertex is 4. It's the first time it's visited, and this one is visited here, and we have an 8. We've visited that vertex. We go to the lowest one, which is vertex 1. It has 2 neighbors. Already we've traveled 4 plus 11 is 15. We're not going to change the 8. 4 plus 8 is 12 to get to vertex 2. We mark this one as visited, and we choose between these 2. We add 7. Now to get from 7 to 6, I add 1 to the 8. Okay, so I've got 8 plus 1, which gives me a 9 here, and 7 to get to vertex 8 is 8 plus 7, which gives me a 15 over here, and that's the only ones that I've got. I'm not going to change that one. Okay, so I mark this vertex as visited. I now pick the smallest one between those 3, which is 9. Okay, from 9 I've got adjacency to this vertex with a weight of 6. So 9 plus 6 is 15, so 15 holds. 9 plus 2 gives me 11 to get to vertex 5. I'm not going to revisit the vertices where I've been, so I mark this one as visited. I now choose between those three, and I see the lowest is 11. Adjacent to 11 is this vertex here. 11 plus 4 is 15, it's already at 12, so the 12 stands. 11 plus 10 is 21, it's the first time we visit that vertex. Okay, and 11 plus 14 is 25, up there at vertex number 3. Okay, so I can mark this one as visited. Now, if I now look at what's left, I've got 15, I've got 12, 25, and 21. If I look at 12, let's start with the smaller one. To get from 12, we have to, in fact, start with the smallest one. To get from 12 to here is 2 more. So that gives me a total of 14, which cancels the 15. So the weight there is 14 at that particular vertex. Okay, then I go to the next one. To get from 2 to 3, I need to add 7. So that's 25, and this gives 19. So already I've changed the 2 and the 19. Now to get from 12 to here, I've already visited. So I can now mark this vertex as a visited vertex. I cannot do anything with 8, folks. 8, I have already visited all its adjacent vertices, so I'm going to mark that with as a visited vertex. I remove the 2 tallies that I had there, which was replaced. So I've now got 19 and 21 left. So if I go from 19 to the only place I can go to now is this vertex 4. 19 plus 8 is 28, which there's already a 21, so I mark it as visited, and there is my Dijkstra algorithm applied. Okay, Dijkstra on the graph was applied to determine the resulting shortest path tree. So if I want to go from 0 to vertex 5, it's a total of 11. Okay, how am I going to move? Well, I'm going to move 8, and this one, and that one. Okay, then I'm at 11. Let's see, 8, 9, 10, 11. Okay, so 8, I add another one to get to 9, add 2 to get to 11. And you can trace the paths between all of the other vertices as well. Okay, folks, I really hope that made sense to you.